Hey everybody, welcome to Module 8. This is actually Module 8 Part 1, where we start to get into a really cool application of multi-level modeling, which is the use of multi-level models in longitudinal or growth models. So we start to move away from just sort of cross-sectional variables into longitudinal ones. It's a very cool application. So let's get into this a little bit more specifically. So last week, we learned how to run and interpret three-level models. So I think we had students nested within classroom, within school, using Project Star as our database. So this week, we're actually going to pivot a little bit, and we're going to start thinking about how to use multi-level models in a growth over time or change over time context. So just to point a little bit about terminology. So we often use the terms growth and longitudinal data analysis interchangeably. And for the most part, that's accurate. But growth models are actually one specific kind of longitudinal model. Longitudinal models are actually a much bigger class that includes any kind of statistical model that includes data over time, repeated measures that are collected from the same participant. So growth models are a very specific kind of longitudinal model that is used to examine change over time. But there are lots of other things you can look at in a longitudinal context. Another thing to point out, growth doesn't always mean growth. This can be a little deceiving. Growth really means change over time in a statistical context. So change can be positive, change can be negative, and change can actually be neutral. So you can test for positive growth, you can test for negative growth, and you can test for sort of no change or neutral growth as well. And all of those things can happen in a growth modeling context. So when you think about growth modeling, you don't always have to think about, I think about like a flower, right? Or a child getting taller or bigger, flower growing. It doesn't have to be that. You can actually look at all sorts of sort of complex longitudinal processes using growth modeling. In all cases, and this is probably something you feel like you've heard before because it's true in all multi-level models, the outcome, the dependent variable, needs to be measured at the lowest level. And that typically means, in this case, since we have repeated measures within each person, the lowest level of our model is no longer the person level. We used to look at students nested within schools, for example. The lowest level in a longitudinal model is actually the observation level, and observations are nested within each person. So it's kind of like we're going down a level, right? We started at the student level. We're actually sort of unpacking the lower level, which includes variability within each person. The nice part about growth modeling is that it builds on top of everything that we've talked about before. So we've talked about models that include random intercepts, and that's really important for growth modeling because individuals typically start at different points on a particular outcome. We don't all start in the same place. That's kind of a natural learning outcome. And that's very easy to do in multi-level modeling. That's a random intercept. And individuals often grow or change at different rates as well. And that is also very easy to model in a multi-level context using random slopes. So all that time we spent kind of building in random intercept models, random slope models, and even three-level models, because if you think about it, a two-level model like the one we've studied, where you have longitudinal data, actually becomes a three-level model because you have observations nested within students within schools or observations within students within classrooms. So everything we've covered so far, believe it or not, does really kind of build nicely into this concept of growth modeling. All right, so we're going to get a little bit into the notation here. I do think it's important to show with you a little bit of the math that's happening behind the scenes. So this is the what's called the null model for a two-level cross-sectional multi-level model. So this is something we've been working with for quite a while, all semester. and hopefully it's starting to be a little bit more familiar. So here we have what are called IJ subscripts. So Yij here, epsilon ij as well. And that means we are looking at a given student, I, who is nested within, for example, school J. That could also be patient I nested within doctor's office J. You know, the context can be variable and change. That's absolutely fine, but you have an individual nested within a context. Our slopes at the bottom level are represented by betas. And at the second level, at level 2, we have gammas for our level 2 slopes. Now, in this case, we just have a 1 beta at level 1, which is our random intercept. And that random intercept is actually decomposed into a grand mean over here, which we're calling gamma 0, 0. Maybe I can get my fancy pointer. So gamma 0, 0. And some variability at the school level, which we'll call U0J or mu0J. And then at level 1, we have this intercept, and then we have some student level variability, which we're calling epsilon ij. So we have 2 random variables that are happening at 2 different levels. We have U0J and epsilon ij, and those are both normally distributed with known variance as seen before. So the predicted score for a given student, student I nested in school J, without any predictors, is now composed of an overall mean, which we're calling gamma 0, 0, plus an individual level random error term, plus a school level random error term. Okay? So those are all things that we have seen before in the format of a null model. So now we're going to look at the notation for a growth model. And it actually doesn't vary that much at all. The big difference, well, a couple things are different. So first of all, we now have TI subscripts instead of IJ. And if you remember in the previous model, I stood for student, and that's still the case here. I stands for the person level. Notice we don't have a J. That would be the school level, although we could do a 3-level model. We've actually learned how to do those, but for now we're just going to look at a 2-level model for growth. Now we have observation T nested within student I, because we have multiple observations collected over time that are nested within student I. And our level 1 predictors are actually pi's, just like in a 3-level model. So pi's are the within person predictors. And before those were betas when we talked about individual level predictors. And the individual level predictors are still betas because now the individual level is just a level higher. It's at level 2 instead of level 1. And if we had a level 3, we would get our gammas. So that pattern still holds the same. Everything basically moves up a level. So we have pi's at level 1, betas at level 2. And the predicted score here is a little bit different because we have a new variable here. We actually have, let me pop back. We have a variable for time. So this is the most important component of a growth model. This is what makes a growth model a growth model. You have a predictor that denotes the time point or the time interval at which an observation was conducted. So one example of thinking about time, maybe you collected data from a student annually when they were in 1st, 2nd, 3rd, 4th, and 5th grade. Their time might be measured as 1 for 1st grade, 2, 3, 4, and then 5. So it's a continuous variable that takes on values according to what grade level or what time point the observation is collected. Time can also be a measure of actual physical time. So if you have very compact data that's collected over a number of hours or days, you might actually be measuring time in hours. So the number of hours since a given time, that's also okay as well. But in this case, and in most cases in the social science, we don't have that kind of intense longitudinal data, although it's very cool, and I do a little bit of that work, and I'd love to talk to you about it. But we typically think about things in terms of waves. So wave 1, Wave 2 might be 6 months later, wave 3, wave 4. And so that is the indicator for time that we're talking about. That is a predictor at the individual level. And then at level 2, we have our equation for the intercept right here. So pi 0 I, which is our intercept, is represented by an overall student level mean, beta 0, 0, and a student level variability in the intercept. We'll call that U0I. And then we also have in our sort of null model or no growth model, we have a predictor of time. And so time is brought down here to the student level. And it is decomposed into an overall impact of time. We'll call that beta 1, 0, plus individual variability in that slope. So this is variability in the intercept, U0I. U1I is variability in the slope. And so we still have our individual term here, which is epsilon ti, and that is variability within student. So that helps to explain variability over time. That is not explained by the measure of time itself or by other predictors that we might introduce at the observation level. So this gets a little tricky, but the key here is this slope estimate, this pi 1 that we obtain, it's actually beta 1 once we account for the random slope, that slope is the measure of growth. So if the estimate of this thing is positive, then whatever it is you're measuring is increasing over time. If the estimate for that thing is negative, it means it's going down. And then if it's non-significant, it means it's not changing significantly over time. So you can test hypotheses for positive, negative, and neutral or null growth over time. So pretty cool, I think, I hope. In terms of the level 1 and level 2 random effects, again, the level 1 error term, epsilon ti, is still distributed in the same way. And now we typically have 2 level 2 random error terms. We have a random variation in the intercept, and we have random variation in the slope. And we can also account for the covariance of those things. If you're an R user, this is done by default. If you're a Stata user, you have to actually specify that option. Otherwise, it assumes that the variation in the slope and the variation in the intercept are unrelated. Okay? So a little bit more, and again, if that's pretty overwhelming, I absolutely understand. This is a pretty tricky concept. This is why we spend 2 weeks on longitudinal and growth models. And in fact, in some places, you can take an entire course in longitudinal data modeling. But this is just to introduce this concept that we have a multi-level modeling framework. Now we have observations that are nested within people, within students in this case, and that we have this predictor at the observation level that tells us the time. The estimate of that predictor essentially tells us about the rate of growth, decline, whatever it is, okay? So I have examples on this slide and the next slide of what this looks like in both Stata and in R. So this may be helpful for you. I'll talk through this a little bit here just to refresh our memory. So this is a model in which all we're trying to understand is change over time in math scores. So we have nested math scores. It looks like we have between 2 and 6 observations of math scores per student. This is from the sustaining effects data set that we'll look at in the demonstration videos. We've got about 1,700 kids measured about 4 times each, which gives us about 7,000 observations total. We fit a multi-level model here with math as the outcome and this predictor year 0 as our, let me pop back. Year 0 is our measure of time. And we have child ID as the nesting variable. So we have observations nested within child ID. And we've included over here a random slope for year 0. So we've included a random intercept and a random slope. This is the preface again. This tells us a little bit about our data structure, about the type of estimator we used, and the likelihood information. And then here is our estimate for growth. It's the estimate for the variable year 0. And what this means, it's 0.75, and it's highly significant. a very high test statistic here. So that means for each increase of 1 year in a child's age, in this case, in between the observations, they're observed a year apart, we would expect a child's math score to increase by about 0.75. And this is roughly a standardized scale. So that's about 3/4 of a standard deviation every year, which is a pretty good rate of growth. These are students in kindergarten to 5th grade. You know, it's a time of pretty aggressive growth in learning in math. And so that kind of makes sense. Here we have the constant. And this is, in this case, the average math score at the first time point, the starting time point in our model, which in this case is kindergarten. So on average, kids start a couple standard deviations below the mean on this measure, and they increase by about 0.7 standard deviations for every year they are in school. So that's positive growth, and it appears to be significant. We also get estimates of the variation in our slope for year 0, which is our growth parameter. So this is the extent to which that slope varies according to person. So that's pretty small, 0.02, a variance of 0.02 on a coefficient of about 0.75. So not a ton of variability in growth, although it does appear that students do grow at different rates. And in terms of the constant, here's our variability. That is much higher, so a variance of 0.67 on an overall constant that starts at -2.7. So children appear to start at very different time points, or very different points in their mathematics learning, and that makes sense too, given what we know, right? Kids come in with very highly variable learning trajectories and also starting points in their learning. And then we have a variable down here, which represents the variability of learning at the within student level, which is the observation level. So we don't have many variables other than growth, which are explaining that right now. Same thing in R. Here is your preface. There's your code. So this again is a model that includes a random slope. So year 0 is included twice. Year 0 is included as a predictor here, and also as a predictor here in the random effects equation. So we're looking at random variability in slope as well as in intercept. R, of course, starts with the random components. So here is the random variability in the intercept. Here is the random variability in slope. And here's the random variability at the within level. And because R automatically includes that covariance between the intercept and slope at the same level, this is the correlation between the random intercept and random slope. It's about 0.1. Which isn't terribly high, but may want to be something we want to include. Again, we've got 7,000 observations nested within about 1,700 kids. And then here are the fixed estimates. These are the growth parameters. So the intercept here again is -2.7. So that's the average score in kindergarten for students in math. And the average rate of growth is about 0.75, and both of those are highly statistically significant. So again, students start fairly low, and they grow over time with some amount of variability in scores. All right, so again, this is just a getting your feet wet approach, getting comfortable with introducing time as a predictor and trying to interpret those growth parameters. Next week, we're going to dive in again a little bit deeper into growth models, talk about nonlinear growth, and talk about just get really more familiar with how these models work. But for now, we just want to expose you to the model and the approach and see a little bit how it works. All right, good luck and have fun.